So I want to give a quick 20-minute rundown of recurrent neural networks. So Toshita has shown you standard feed-forward networks, and I want to basically, first of all, motivate why recurrent networks are interesting and exactly what they are. And then I want to just give two quick applications of, first, a very simple example where you do integer addition, where the integers are represented as just a sequence, and then a more complicated example in terms of question answering. Okay, so first of all, why do we even need recurrent networks? So suppose you have a task, a machine learning task, where you need to do something like this. You have a list of characters, and you want to predict what is the next character after this one. So for humans, this seems fairly simple. You can quickly auto-complete this and say, oh, the next character is probably a G. So the difference between this sort of problem and the previous ones that, like, for example, classify, well, actually, this is, yeah. So the difference between this and with feed-forward neural networks is that you have to have some concept of sequence or order. So these characters, if you just put them into like some bag and said, okay, what is the next thing? You've got no idea. You have to know that W came, then H, then Y, etc. So recurrent networks are one way of dealing with problems where the order matters. Okay, so before I show you exactly what recurrent networks are, I just want to motivate so that people are interested actually in this stuff. So why do we even care about recurrent networks? So first of all, there's lots of applications. So all of these applications that I'm mentioning now, they are the state of the art for recurrent networks. So things like speech recognition, which in the past used all kinds of other techniques that are very complicated. Now the best systems all use recurrent networks. So an example would be Baidu's Deep Speech 2. And by the way, these notebooks will be made available after this presentation, so you can get access to all of the links that I'm going to give. So yeah, for speech recognition, speech synthesis, there's a very nice demo that Google has on this. So synthesizing speech from text that makes it sound like a normal human voice. To obviously, Etienne touched on this already, so language translation. And just for interest, Google Translate, they switched over to using recurrent networks last year. So previously they used a very different kind of system, and it changed completely how good the translation service became. So there's a nice New York Times article on this, and one random example is that this particular thing. So as dawn broke over Tokyo, Google Translate was the #1 trend on Japanese Twitter, just above some cult anime series and the long-awaited new single from a girl idol supergroup. Everyone wondered how had Google Translate and the network describes what's happening in the image. So the network generates a person riding on a motorcycle on a dirt road. Okay, and then the last thing that I'll just mention some examples of, so things like question answering. So a very important task in natural language processing is that you give the computer like a piece of text, and you can ask questions about the text. So you give the network both the context and then the question. And then you want the computer to make a prediction. So this is a real-life example. There's a very nice data set that you can look at later. And this is a prediction made by Match LSTM network. And you can click on this link, and there's many more predictions, and you can see how this network performs on this data set. So there's many other applications, from sentiment analysis, like is this a positive sentiment for a movie review? Language modeling, where you want to predict, for example, what is the next character in a sequence of characters or words, or time series prediction. So there's many data sets, for example, like stock market data or whatever else you want to have, where you want to predict the future in some time series. All of these sorts of tasks are where recurrent networks are extremely good. And for some of them, like there's basically no competition at the moment. For things like question answering or speech recognition, there are no alternative methods that can compete. Okay, so the other reason that they're interesting is that they are arbitrarily powerful models. So this is a bit of a technical thing. Okay, I don't know why this became so small suddenly. I'll reformat it later. Okay, so basically, these are the two sort of foundational theorems for neural networks. So for feed-forward neural networks, the ones that Toshita showed you, there's a theorem that says that they're powerful enough if you have enough neurons in the network or enough parameters in the network, they can approximate any continuous function arbitrarily well. So they're powerful enough to basically learn anything if you're predicting numbers, for example. And there's a very similar theorem for recurrent neural networks, that they're Turing complete. So any sort of computation can be simulated using recurrent neural networks. The difficulty, though, is obviously training them to do anything, and that is the next sort of task. Okay, so what is a recurrent network? So given that we've motivated this now, so they're extremely powerful models. They can model any sort of programs. But what exactly are they, and how do they work? So I want to just show how simple they actually are. They are extremely simple models that can give rise to this extremely complicated behavior. So the simplest recurrent network looks like this. So you basically have a layer, this A over here. It takes in some sequence time step, produces some state, and then it uses that state again, and it feeds that back into itself, and then it processes the next time step. So this is perfectly equivalent to unrolling. So what that means is that we can always see something with a feedback loop as a computational graph that is many steps. So in this case, this x0 means like the first element of the sequence. And this obviously applies to sequences, this whole thing. So the first element of the sequence comes into the network. It produces a state, h0. That state at the same time gets fed into the next time step. And the same module, and by same, it also means it's using exactly the same parameters. So those parameters are fixed. So they're exactly the same across this entire sequence. This recomputes it with the next input of the sequence, so on and so forth. So what you really get from this is that you give it a sequence, so x0, x1, x2, and it returns a sequence of states, h0, h1, h2, etc. So that is fundamentally what recurrent layer does. So I wanted to show how simple this is to actually implement. So, and this is useful to see, like if you're looking at this later on. This is a recurrent layer. So all that it's doing is it's got an input. So each time step, it basically takes in some parameters. So it takes in a matrix of weights that get applied to the states, a matrix that get applied to the inputs, and it's just the dot product with the state, the dot with the input, add some biases, and then take the tan of that. So that's one time step. So this function is one of these modules. And all you do then is that there's a function in Mathematica, fold list, which just applies this guy. So it starts with an initial state and an input, and it applies this guy again and again, and it feeds back the state back into itself. So that's it. And we can compare this with the Mathematica implementation. So Mathematica has an implementation of basic recurrent layer, which is called just basic recurrent layer. We can give it some input. So we can say, let's give it a sequence of length 3. One important thing is that these recurrent layers, they only take vectors. They take sequences of vectors. So it has a sequence length, and then each of the vectors inside the sequence has a feature size, so 2. So in this case, it's a sequence of length 3 of vectors of size 2. And this is up to you, to the user, to choose what the state size is of the RNN. The bigger the state size is, the better it can remember past events. And just as a reminder quickly, the states are these guys here, and they get fed back into the next level. And obviously, like if this is a very, very small state, there's very little information that it can keep passing on in the sequence. So it can't remember what happened previously if it's too small. Okay, and we can initialize this basic recurrent layer. Here's the layer. We can click on this and see what this looks like. The input, what is this here? The input is here, a sequence of length 3 of vectors of size 2, and the output, the sequence length, it's going to be a sequence of 3 states, basically. Okay, and then we can also extract the parameters if we wanted to, and we can then evaluate this layer, the one we've just defined, with the one we implemented in Mathematica, the one that we just did in the previous slide, and they're exactly the same. So that's how simple this is. Okay, so the next step is people might have heard about long, like LSTMs or GRUs, etc. So the simple recurrent layer, that is what people originally started with as a model for modeling sequences. However, they had some problems. So people had a lot of difficulties training them. Like they just would stop training. They wouldn't do anything interesting. And if you recall how we train neural networks, it's always about calculating the gradients. So for the key insight is that a recurrent network is basically a very, very deep feed-forward network. So we can actually visualize, there's a hidden function in Mathematica that we can actually visualize the actual unrolling operation on anything, or any layers. So these are like the small primitive operations, like these are the linear layers, these are the parameters, and we can say we want to have this like a sequence length of 1, this gets unrolled for one sequence length, or if it's sequence length of 5, oopsie, then you can see that these 5 steps are basically, it's just a normal network with one feature that the parameters, you can see these are the weights, they are exactly the same at every time step, just the same ones repeated again and again. So what people realized was that, and this applies to any feed-forward networks, is that if you have a very, very deep network, so for example, like you might have a sequence length of 100, this becomes super, super long. And the gradients, they exponentially vanish or explode with the length of the depth of the network. And people thought that this was basically a fatal blow against training these things. So what would happen is that you can imagine like the gradients, there's a loss function going to be at some point at the end, and the gradients have to propagate through all these layers. So this is still a very small network, like 5 layers. But when it gets to like 100, the gradients start just disappearing or they start blowing up. It's very, very sensitive to all kinds of things. It's very fragile. So this was termed the vanishing exploding gradient problem, and this was discovered by Hochreiter in 1991. And the main solutions that people came up to solve this problem, well, there were a bunch of solutions, but the ones that were very good and had very good theoretical properties was to modify the internals of the actual layer. So for the basic layer, there was just an input. There's some matrix operations here that combine the input and the previous state, and there's a tan H, and then it just flows through. So people, or there was a discovery made that if you make a modification to this thing and add another state, you can prove mathematically that this now no longer suffers from the vanishing or exploding gradient problem. So it has a much more complicated structure inside, but the idea is exactly the same. You just have multiple of these modules and you just repeat them across the sequence. So you can see this takes an xt minus 1, then xt, then xt plus 1. Okay, so that's the motivation for having these other ones. And there's lots of variants of this. So there's LSTM, or long short-term memory layer. There's a gated recurrent layer, which we have in the system as well. And we also allow people to actually define their own modules like this with netfold operator. So if there's something in the literature, like a new module like this, you can very quickly define it, and then it'll work across sequences. Okay, so the major recommendation, though, from this whole thing is that if you want to have very stable training, it is better to use long short-term memory layer than basic recurrent layer. So for the examples that I'll do later, I'll only use this, or gated recurrent layer, because they solve this problem of vanishing or exponent gradients. And you should really read, like, if you really want details about this, I can't obviously go into that right now, but I give references to things like this paper, which gives a good explanation of the technical details. Okay, so that's the major thing. So the recommendation, use special layers or special recurrent layers that don't suffer from this training instability. Okay, so now I want to actually just show an example of this. So the very simple example, which is many frameworks use this as a sort of canonical example of sequence learning, is the addition problem. So the problem is very simple. You give a string. So this is just a pure string, like this is nothing else. And you define a net encoder that works on characters. And we can actually try out this encoder now on, let's say, this guy here. So this encoder just basically decomposes this into a sequence of integers that represent the classes. So there's 9, 7, a plus, 60 plus 0. If I have another plus here, it will be 11 and 11. So this is a classic thing. We need some representation for categorical variables, which we're treating these characters to be. Okay, so we have this net encoder. So the learning problem now is, given a sequence of these guys, predict what the actual sum is going to be. So, and this sum is now, that's a number. So that seems interesting. And it obviously everything, you can't just you can't look at these separately. Like, it requires you to say, okay, this 10, this is followed by, the 9 is followed by 7, then followed by plus, then followed by 6, etc., etc. So we define a very simple network that can do this. So the network goes like this. So there's a long short-term memory layer. The state size, there's no good rules about how big this should be. You should basically experiment with it until you get something that's big enough to fit the problem properly. So the way that this works is that there's one of these. So it takes in a sequence. We can actually see from here. So it says a sequence of these indices, and they're all between 1 and 11. And it then produces, and these ends here, they mean that the size has not been determined yet. So we have very good support for variable length sequences. So you can add data here that is not the same length, and it goes through the long short-term memory layers, and there's 2 of them. Each of them produces another sequence. And then at some point, because we want a single number out, we need to get rid of the sequence, right? Because we want to predict a single number. So what's very common is that you use something called sequence last. So all it does is it just takes the last value of the sequence, and it says that is our representation now. And the next layer is going to have to use that vector to make a prediction. There's many ways of getting like a vector out of of this thing, because at some point, you have to go from sequence to number, and this is a very common way of getting out or getting rid of the sequence. Okay, so that's defined, and then we can train the network. We can also just take a validation set. So this is a special syntax where you take 10% of the data as validation. Okay, so it's training. You can see the scaling looks very strange on my screen. This doesn't usually look like that without a presentation mode. Okay, so it's training very, very nicely. Maybe just let it go down a little bit more. Okay, so this could train for a bunch more. At some point I should just stop it. Okay, I think that's enough. So I can always stop the training and it'll give me something. So this is obviously not as good as it can be, but we can already see what it can give us. So 10 plus 25, it gives us 35, perfectly correct. 9 plus 11, it's slightly wrong. And I'm rounding the numbers because this is predicting actual real numbers. So you might as well round it because we've only got integers here. Or we can just leave it like that, and you can see what predictions it makes. This one is actually perfectly correct. So that's it. It's as simple as that. So this was basically a classification, or this is actually a regression problem that takes in a sequence but returns just a single number. Okay. A slightly harder problem is question answering. So I'm just going to get the data. This is a data set that Facebook released called Babby. Something is frozen here. Okay, there we go, unfrozen. Okay. So let's get the data, and we'll have an example of some of the data. Let's see. So this data set, it's designed to be as simple as possible for question answering. So you can look at, you can look this up on Google. They're basically toy problems, but it's basically, they call this a prerequisite task. So things that do question answering, they should be able to solve this task before solving harder tasks for question answering. So yeah, but for this purpose, this is fine. So here's an example of what this looks like. You get a context, you get a question, where's Daniel, given this whole spiel, and you get given an answer. So we can, first of all, get a list of all the words that are in the questions and the contexts. And then we want to get the classes out as well, the things that are being predicted and the answers. And then we want to have a net encoder that can convert these words into tokens or into integers. So let that run. You can see that the list of classes is pretty simple in this case. There's only like 1, 2, 3, 4, 5, 6 classes. And let's do this. And here's our token encoder. Okay, so the network to do this is the simplest possible network for something like question answering. So I'll walk through quickly how this works. So the idea is that you need to have 2 inputs, so one for a question and one for a context. So you can see we've got something for the context. So it basically is an embedding layer which creates a vector representation from integers. There's some regularization dropout to prevent overfitting. And the question term is exactly the same. Embedding layer, dropout layer, and then this one actually has a long short-term memory layer as well. So the idea is very simple. It's that the question comes in, it gets processed by the question network. Okay, I'm not sure why this is not clicking open. And then the same happens with sorry, where's this here? Yeah, so the question comes in, the context comes in, we get some representation of that, we catenate them together over here, and then we can, we also take just the sequence last, like as we did previously, so we get a single vector representation of the sequence for the question, because the question is, yeah, it's a sequence as well, and these sequences are different sizes, obviously. And then we can just feed that into the classifier, which is exactly the same as the previous one for addition. So the classifier is just a long short-term memory layer, and then a sequence last layer, dropout layer, then the linear layer with the number of classes that we've got, and then a softmax. So it's as simple as that. And then this stuff is just how do we connect them. Okay, so that's a fairly simple network, and we can train it. We can just give it our data, give it a validation set, and some training rounds. Okay, so whilst this is training, there is in the nettrain documentation, like I might as well sell this whilst this is going on. So the nettrain documentation has an application section, and it has a lot of examples of things. So whilst this is going on, I can just show you this quickly. So nettrain. So there's an applications example thing, and for a lot of recurrent network examples and for some very complicated ones, you should see these examples here. Integer addition, there's 4 different types. Sorting sequences, question answering. So there's this particular question answering method, but there's also a memory network implementation, which is a lot more complicated. So it has a much more complicated network. To all kinds of other examples. Okay, let me switch back to the... Okay, well, it's done some training. It'll still improve a lot, but I don't have the time to keep training. So I'll just interrupt it now and then use it as it is. So we'll see if it actually does anything interesting. So let's see. So this is the context that I can give it. And this is from the test set, so it hasn't ever seen this example. So that will be cheating if I gave it something from the training set. Let's see. So its answer is garden. So where's Daniel? The last thing that Daniel did is Daniel went to the garden. So that's correct. And we can also calculate the accuracy on the test set pretty easily. Okay, in this case, it's only getting 52%. So with the memory network, you get about 99% accuracy. So this method is very naive, as you can see. Okay, so that is a simple and very quick introduction to recurrent networks. As this notebook will be available to people, I wanted to also just give a section on where people can learn more if they want to, because this is, yeah, like your understanding might not be very deep after just a single talk like this. So these are some resources that I found pretty good.